Hello to our presentation of progress update video for energy challenge of the Automotive OGO. We're going to start with a bit of background about the project. Traditionally, the world of automotive has also been about internal combustion engines and a very efficient way of working, but these days there's a lot of modern innovations, especially looking at hybrid cars which implement electric motors or just fully electric motors, like Tesla is doing right now. The problem statement or the project goal of this project is to develop and demonstrate a driving strategy that yields minimal energy consumption for the model car. We're going to do several experiments on our model car to have the forces be the resisting forces as low as possible and have the optimal drive line. There's also one extra assignment outside of this project goal, and that's to add a toll payment system with the help of an infrared signal and a radio transmitter. We have a certain work approach for the project. We're going to do all the work at least in couples, so we can always work together and ask questions to people that we work together with. This is to check each other's work, and we do the checkup in different ways. First of all, by working couples. We also do work on each other's, or check each other's work through presentation updates we do on Tuesday during our meetings. And we also work on a logbook in our online workspace, so we can check up on each other's work when we have time to read through the work that they've done, with given dates and their goals for the next meeting. We're going to talk in this presentation about a few things that we're experimenting on and working on in this project. We have 3 experiments. The first experiment is the wind tunnel experiment. This is to determine the air drag coefficient of the car, and we're going to do several iterations by modifying the car and without modifications. Our second experiment is the rolling resistance experiment. This is to determine the rolling resistance coefficient and to see if we can work around certain resisting forces to have as efficient car as possible. The third test is the dynamometer experiment. This is to experiment on the efficiency of the car and the efficiency of the energy output, so through the electromotor and also the auxiliaries of the model car, and see how we can be as efficient as possible with our energy consumption. Like I also mentioned, the toll payment system is one of our bonus assignments. We're going to do this using an infrared signal sent by the trackside that we get from the project management, and then we have to make a transmitter, a radio transmitter that sends back a signal that we have received the infrared signal. And to implement all of this in our model car, we're going to do some Arduino programming. There's 3 main tasks in the Arduino programming, considering of the LEDs, the RPM sensor, and then implementing everything together. And then we're going to conclude everything mentioned.
Alright, Jerry and I were assigned the wind tunnel experiment. What we've done so far is, of course, we've done research. We've read through the documents on Canvas, but we've also researched online. We've looked at what influences the air drag on a car. The experiment itself has to be done on the 4th of December, and we've prepared properly for that experiment. What we're going to do is determine the air drag coefficient for different setups, and as you can see here, we have multiple modifications that we want to experiment with. We're going to do the experiment without modifications, so we get a standard air drag coefficient for the car. We're also going to add a front splitter and a spoiler, so we measure the difference that these modifications make to the air drag coefficient. Furthermore, we're also going to add some tape to the car to block a small block on the car, which can increase the air drag coefficient, which is negative. And when we've finally determined the air drag coefficient, we can create a tank-to-wheel analysis we can add up the different forces that influence the car, and we can see what percentage of the forces that work on the car have to do with the air drag. So here we have a schematic of the air drag experiment. What we're going to do is place the car on a suspended platform, as you can see here, and the wind tunnel will be activated so that the air flows through the wind tunnel and acts on the car. The platform that the car is suspended on will move, and the force will be locked by a sensor which is attached to a wire and the platform.
The second experiment that we're going to do is the rolling resistance experiment. The work that we've done so far is, of course, mainly the research that we started with and then preparing by using a test plan. The experiment is done on the 5th of December, and the main goal of this is to find the rolling resistance coefficient, and we're going to do this by using the coast down test. A coast down test is basically implemented by just giving the car a certain speed and then letting it roll out to see how much this deceleration is. And from this deceleration we can calculate the total resisting forces. And when we get the results of the air drag test of the wind tunnel, then we can subtract those forces and then we're left with the rolling resistance forces, since there's no gradient on the Markthal where we're going to test, do the experiment and also do the final challenge day. We're going to do this deceleration, we're going to log this with the help of the RPN sensor given to us by the project management. And it's just a basic schematic of the rolling resistance experiment, is that we're just going to push the car forward, giving it certain velocity, and then at time t is 0, we're going to let the car go. So it's just going to roll out or basically coast down till it stands still. And at standstill we can then make a velocity time diagram to calculate the deceleration, and with the help of deceleration we can then calculate forces.
So the third test we are going to do will be the dynamo meter test. This experiment will take place on the 3rd of December in the morning from 9 to 10. What we've done so far is we've done research on Canvas, on the internet and on other places to get more info about what a dynamometer is on itself. This experiment will be divided in 3 different tests. The first test is already done by the crew of the dynamometer itself. This first test is about knowing the rolling resistance on the dyno, because the dyno is a tire on metal, so the rolling resistance coefficient is different. The second test is all about knowing the efficiency of the drivetrain and making a tank-to-wheel analysis. In this test, we will measure the input power and the output power of the vehicle. The input power will be done and calculated by knowing the electrical input, which will be the ampere and the voltage, and the output power will be the torque and the rotational speed of the tires on the dyno. The third test will be about knowing the power consumption of the auxiliaries. The auxiliaries are a kind of accessories which consume power but don't provide to the drivetrain of the car. In this test, the car will not be moving, the motor will not be producing any power, so the only force that's consuming power from the battery will be the auxiliaries. So what we have to do after this test, we'll be doing the experiments that will be done on the 3rd of December. And after the test or the experiment, we will need to work out the results from this test. So, to get a visual representation of the test, this is the third test where the engine is turning and the dyno is turning. On this, this is the dyno, this is the vehicle, this is rotating, and because of this you can calculate the rolling resistance of the car. This is the second test. In this, the engine of the motor, the motor will be turning. This will consume power from battery. There will be an input. It goes through the drivetrain to the tires. These will be turning. The input power will be different from the output power. This means there is a certain percentage of loss of power through the vehicle, and this means this will be the efficiency of the total drivetrain. So we know the total efficiency, and the third test will make the efficiency even more correct, because with this test we will calculate the auxiliary power, which will be consumption, and if we subtract the power lost due to the auxiliaries, we know how much power is lost elsewhere within the drivetrain, and so we have the total efficiency of the car, and we can make a proper tank-to-wheel analysis of the vehicle.
Right. So after the wind tunnel test, we can focus our attention on different tasks. And one of those tasks is making the toll payment system. So as we've worked on the wind tunnel test, we haven't made that much progress on the toll payment system, but we've done all the research that is needed to complete this system. We've also already started on making the circuits, so the toll payment system is coming along nicely. The toll payment system, or the goal of the toll payment system, is creating a system which measures the time taken to take a lap for the car, but also send or measure the laps, the time it takes to take the laps, but also how many laps we've taken so far. The toll payment system consists of two components: an infrared sensor and a radio transmitter, and both of these components have two sides: the track side, which you can see here in this schematic, and the car side. The infrared sensor, or the track related infrared sensor, sends a infrared signal parallel to the finish line of the track, and the car receives this signal, but to compensate for all the other possible infrared signals that exist in the world, there is a filter that filters out all the other frequencies of infrared signals, so we only get the signal that is related to the track. The other part is the radio transmitter. This also consists of two parts: the track side and the car side. So when the car passes through the infrared beam, it emits the car identification code, and when the track side receives this code, it starts timing the lap, and it also counts how many laps the car has already made, and it will send this through the GUI, which is basically a system which can show the data in a coherent way. And here we also see the circuits and a small schematic about the track side and the car side.
So coming to the Arduino programming, the work we've done so far is all about programming the LEDs and discovering how the LEDs could be programmed. Coming to the RPM, we haven't done yet so far on it because we have focused more on the LEDs itself. And we currently now know how we can program it using the ledge, the SDI or serial data input, and a clock cycle. We first have done research, or Abel has done research on the LEDs. After that, he started to figure out and made some sketches on how he could time those three inputs correctly, so the output we want is expected as we want it wanted it to have. So he has been sketching, he has been discovering, and he has been doing research on it. What we have to do now is mainly focused on how we can combine the LEDs with the results from the experiments, like the dynamometer. And what we also have to do is program the RPM sensor, so with the output from the RPM sensor is what we want to have, and we can combine it with the results from the other experiments. So this is like an example from what we've done. This is like the RGB. We've coded it so it only shows one color. We've also coded it differently that it like goes from left to right, left. It just turns, it switches colors. We configured it, we made sketches of combining these three colors, so we get a color white, or we get different colors.
And then we come to the conclusion of the work that we've done so far. So if to summarize real shortly, we've mainly focused in the beginning on the test plans, and since that was close to the deadline. We've done all the research on the experiments and then made the test plans and submitted them. So on the extra assignment of the toll payment booth, we started the research and also started with the first circuit, which we can then test to make the eventual circuit for the infrared scanner. The Arduino programming has been a bit challenging because it's a new coding language, but we're making real progress, and now we're gonna go to the next step for the RPM sensor. And so our work done so far is given, and our future plans is then by doing the experiments, by progressing the results that we have gotten from the experiments, and then finishing up the program of the Arduino and of course the toll payment booth. In the given time frame, we should be done next week or in week 5 with all the experiments, and if we then have the results, we can implement those in the Arduino programming, and then that's the only thing that we're going to focus on for the last couple of weeks. And of course then the challenge day and the final report that we're going to hand in. And this should be all feasible in the given time frame that we've gotten, and then the project should be done properly in the end.